Every massive internet-scale system you use today begins its life exactly the same way, as a single, overworked server. This schematic outlines the initial request flow. When a user navigates to a website, they use a domain name, which the browser must first resolve by contacting a third-party domain name system. Looking closely at Step 2, the DNS translates that domain and returns a specific IP address. In this example, 15.125.23.214, back to the client. Armed with that exact IP address, the user's device sends a direct HTTP request to the web server hardware. The server processes the request and returns the required data. For mobile apps, the output looks like the JSON payload shown here, returning fields like user ID, first name, and postal code. A web browser, alternatively, receives a fully rendered HTML page. This setup is elegant in its simplicity. Everything, the application logic, the database, the cache, runs on one machine. But as traffic scales, that simplicity becomes a critical liability. When a sudden, massive spike in traffic hits that single IP address, the system chokes. Inside, the server attempts to handle strictly conflicting tasks simultaneously. It evaluates business logic, serves static images, and queries the database all at once. Web application processing requires high CPU cycles, while database operations demand heavy memory and disk I/O. Forcing them to share the same hardware leads to immediate resource starvation. The physical limits of the hardware are quickly reached. The CPU maxes out at 100%, and the system begins aggressively thrashing its memory. The server stops accepting new connections. Existing requests time out, and users are greeted with a wall of 502 bad gateway errors. This is a single point of failure. If this one physical machine loses power or overloads, every user is disconnected and the entire business goes offline. The immediate solution to an overloaded monolith is not to buy a larger machine, but to divide the labor. This diagram illustrates the first architectural split. We separate the web tier from the data tier. The traffic flow becomes linear. The user contacts the web server, and the web server issues read, write, or update commands directly to the database. By decoupling these components, we align the software with its required hardware. Web servers can be optimized for raw compute power, while database servers can be loaded with massive amounts of RAM and fast solid-state storage. Establishing distinct web and data tiers allows each layer to scale on its own terms, independent of the other. Creating a dedicated data tier forces an immediate architectural decision. What type of database model should store the user's state? The default industry standard is the relational SQL database, which organizes data into strict tables and rows. For the vast majority of development teams, SQL is the correct choice. It boasts over 40 years of maturity and guarantees strict consistency across related data points. The alternative is the non-relational NoSQL database. NoSQL operates without strict tables, making it the preferred choice only for highly specific use cases, when the application demands super low latency, when storing massive amounts of completely unstructured data, or when directly serializing JSON objects. Selecting the wrong data model for the specific traffic profile at this stage will create severe friction when attempting to distribute the load across multiple machines later. Even with decoupled tiers, continued user growth guarantees the new separated servers will eventually hit their own capacity limits. Engineers face two paths. The first is vertical scaling, or scaling up, adding more CPU, RAM, and disk space to the existing server. But vertical scaling has a hard ceiling. It is impossible to add unlimited compute power to a single motherboard. More importantly, it retains the fatal architectural flaw of the monolith. No matter how powerful the server is, it remains a single point of failure. The alternative is horizontal scaling, or scaling out. Instead of buying one massive machine, you distribute the compute load across a pool of smaller, cheaper servers. While vertical scaling buys temporary time for small applications, horizontal scaling provides the redundancy required to build a highly available system. Scaling the web tier horizontally introduces a new routing problem. With 3 web servers instead of 1, the client no longer knows which specific IP address to target. This architecture inserts a load balancer, sitting directly between users and the web tier. clients connect to the load balancer's public IP. The load balancer acts as a traffic cop, routing HTTP requests to either server 1 or server 2 over private internal IPs. This component creates high availability. The load balancer constantly monitors the health of the web servers beneath it. If a server crashes or goes offline, the load balancer instantly halts traffic to the dead node, automatically distributing incoming requests to the remaining healthy machines. The web tier is now highly available. If traffic spikes again, engineers simply drop another server into the pool and the load balancer absorbs the volume. The compute load is now distributed, but the architecture below the web tier remains unchanged. Despite having multiple web servers, they all still point to a single database. This single point of failure remains the primary risk for the entire stack. We apply database replication, splitting the database into a master and a slave. This enforces a strict division. Data-modifying actions are routed exclusively to the master database. Read queries are routed to the slave. Distributing reads in parallel drastically improves query response times. While effective, replication introduces immediate operational complexity. Data must constantly sync from the master to the replicas, and if the master fails, a replica must be promoted to take its place without losing recent transactions. This blueprint captures the architecture required to survive heavy traffic. We've scaled to an infrastructure featuring DNS, a load balancer, a web tier, and replicated databases. A request travels a resilient path, resolving the domain, passing the load balancer, processing statelessly, and retrieving data. We have successfully decoupled compute from state and enabled horizontal scaling and ensured that the failure of any single physical server will not bring down the application. But escaping the single server bottleneck is only the first step. As traffic grows from thousands of users to millions, the sheer physical distance data must travel will force us to introduce aggressive caching strategies and global content delivery networks.